Since 1995, almost 400,000 earthquake-related deaths have occurred worldwide. Seismic activity is capable of causing economic and human loss due to failures in buildings, bridges, and lifeline systems. In the U.S. alone, economic losses due to seismic activity amount to approximately $4 to $6 billion annually. Small earthquakes occur every day. Larger and more damaging earthquakes, although happening less frequently, occur on average of once per decade. Earthquake activity cannot be prevented, but through the continued efforts of earthquake engineers, we have both learned and applied how to design and build structures to better withstand seismic activity and ensure the continuation of our society.
The goal of the Network for Earthquake Engineering Simulation Consortium is to accelerate progress in earthquake engineering research through the integration of people, ideas, and tools in a collaborative environment.
The NEES Consortium is named after George E. Brown Jr., a congressman from California that dedicated his life to seismic safety.
Well, NEES was really outgrowth of what the United States witnessed during the 1989 Loma Prieta earthquake and the 1994 Northridge earthquake. There's a lot of devastation done on the West Coast as a result of those earthquakes. And so there was a presidential order then to take stock of what is the experimental facilities in the United States that could be used to help mitigate against such losses in future earthquakes.
There's several different parts to NEES. There's the 15 experimental sites, and these are 15 earthquake engineering laboratories that are located all over the country that won an award to provide a substantial improvement to their ability to conduct research. Then there's NEES IT, which is the NEES Information Technology Infrastructure, which is, in a sense, the information technology glue that binds the sites together and creates a lot of other shared resources and information technology abilities that every single site is able to use and benefit from.
The goal of NEES is to accelerate the rate of progress in earthquake engineering. And we expect to accelerate the rate of progress by having much more collaboration and shared knowledge between these facilities.
I'm a researcher, and for me NEES is like a cool toy, and there's so many cool things you can do that I'm still trying to figure out what are the useful things to do.
I'm quite proud of having this equipment, being able to share it with others, letting remote researchers get involved.
Improve the way we build things and hopefully save lives in the future by building safer structures.
And then we have NEES Inc., which is the coordinating organization for all of the activities and is the central point of contact for the National Science Foundation.
In many other centers or institutes that may have focused on earthquake engineering or do focus on earthquake engineering, they're in one place, and all their resources, all their people, their equipment is in one place. We are a distributed facility. We are spread over 15 universities, and we're in the process of expanding that network. So we're called a distributed network or distributed collaboratory rather than a center or an institute.
We try to coordinate, pool resources and coordinate and make the best use of both dollars and information.
The financial advantage here is tremendous. The cost of doing the experiments within the NEES laboratory are not minimal. This is large-scale testing, so specimens are costly and it takes time to build specimens. By running experimental tests and generating data from those tests, in the simulation process, in the computer process afterwards, we can run additional simulations of that test with changing variables without the expense now of building additional large-scale specimens and the time involved.
It's kind of a new concept. The classic university style of research is that a researcher does research and publishes. NEES tries to pull that together and share information, data, knowledge, so we can solve bigger problems. We can change the way we do research.
I think one of the most unique aspects of NEES is the fact that it brings together multiple institutions. Instead of it being one institution trying to attack an earthquake engineering problem by itself, You have a group of laboratories that are being brought together to try to solve major earthquake engineering problems that we haven't been able to solve before.
Of the research we've done so far, I think clearly the most impact has been the work that we've done on hospitals, older hospitals for rehabilitation in California. We've been able to do work that probably will save clients tens of millions of dollars over the next 5 years. And that's a really satisfying project to be involved with here.
NEES field and mobile facilities include UCLA, the University of Texas, Austin, and the University of California at Santa Barbara.
This is a site where we actually monitor the ground motion at different depths in the soil, all the way down to the rock at a half a kilometer's depth. And we can actually monitor as the earthquake happens, the waves propagate up through, and we see it hit the deepest sensor first, and then propagate up through all the other sensors, all the way to the surface. So we're trying to be able to use that information to improve our techniques for simulation of future earthquakes. And the reason we're out here, there's not many buildings around us, but the faults are here, and we know we're going to get large motions, and that's really what we want to understand, is those large motions.
So we have a collection of these to measure the shaking at various spots in the soil and rock below us. And the soil here is about 20 meters or about 60 feet deep. Below that it's hard granite. So we're measuring how much the soil actually changes the motion that comes from the earthquake.
You know, we have a pretty good idea for how the waves propagate in the rock, the hard material. But as you get up into the soils, the waves change. They amplify sometimes, other times there's de-amplification, and so trying to understand that and how we might build structures to be able to withstand the shaking that comes from earthquakes.
The signals from all of these sensors get carried by cables into the building that you see behind you. That's where the brains of this observatory are. That's where all the data acquisition is, the data transmission facility. We are recording the data continuously. Not just here, but the data are being sent by radio link through Internet 2 and through the NEES cyber infrastructure to allow us to get real-time data, to get the continuous data, so that if I tap my foot here, I can see it on a computer in Santa Barbara and record it on a computer.
The structure behind us, it's a very simple configuration. It's a cube, basically, 4 meters on a side and 4 meters tall. And we wanted it to be simple so that what we could study was the interaction between the soil and the foundation and structure without having lots of structural behavior that's due to a odd shaped structure. And so it's made simple for a purpose so that we can understand how the structure interacts with that soil during strong shaking.
Behind us we have the NEES at UCLA, what we call our mobile command center truck. Inside the truck here we have computers that control the antenna, that control the transmission of data. Over there is our data acquisition system, just over here. And that's all going, sending data in real time to computers inside the truck, and finally through the antenna back to UCLA. And we have a nice office for the people who are actually doing the experiment to work in any kind of field condition. We can move this to the field like this. We can put it next to a building that we're shaking, or we can put it on a dam or a bridge that we might be investigating. So this allows us to essentially take an office and a laboratory out to the field.
NEES shake table facilities include the University of Buffalo, the University of California at San Diego, and the University of Nevada at Reno, which has 3 biaxial shake tables that function in unison or independently.
Well, this facility is very special because it's the only laboratory like it in the United States, and probably in the world, where we have 3 shake tables. Three large shake tables, each one of which can replicate earthquakes at large scale. These tables can each carry 50 tons. They can move large displacements. This one is 12 inches at very high frequencies, representing real earthquakes at large scale.
And what we hope to find from this research is to learn about interaction among different components of a bridge. This is a system test, whereas all the previous research that has been done in bridge earthquake engineering were primarily on component tests, on single columns, maybe 2 columns, usually single columns.
What is unique about this facility is that we can test an entire bridge system. So it's a bit like the leg bone and the thigh bone and the hip bone, rather than just looking at the leg bone alone. Because just looking at the leg bone alone, you don't learn a lot except the strength of the leg. But how it all goes together and how it creates the whole ability of us to walk. You have to look at the whole system, the skeleton. Same with the bridge.
The testing that we're doing right now is the conventional materials like the normal concrete and the rebars with the conventional ratios steel. Now in the next 2 specimens we'll understand the response this time, and then in the next 2 specimens we'll see what kind of innovative material can we use. So it's going to be phases. This is the first experiment. We'll be looking to do 2 more in the next couple of years.
In one of the bridge models that we'll be testing, we're going to try materials that haven't been tried in earthquake engineering. We're going to use nickel titanium material instead of steel. That's exciting.
Yesterday afternoon, and that bridge was banging into the abutments, pounding into the abutments. The sound, the dust, the spalling of concrete. You can't help but say this is better than Universal Studios. Better than the earthquake ride at Universal Studios. This is real life, and this is real concrete failing, and these noises are not artificially generated. This is what happens in an earthquake.
NEES Geotechnical centrifuge facilities are located at Rensselaer Polytechnic Institute and the University of California, Davis. UC Davis features a 9-meter centrifuge that can spin and shake models of soil layers and soil structure systems.
This facility is used mostly for geotechnical structures that involve a lot of soil, like earth dams, foundations for buildings, retaining walls, foundations for bridges. A lot of the problem involves soil, usually. And so the purpose of the centrifuge is that it can increase the stresses on the specimen. So we load a specimen on the end of the centrifuge, and then the centrifuge spins around, and the centrifugal force increases the pressure on the soil.
What we hope to gain from that is a better understanding of what's going on during the earthquake, so that we can better design structures to withstand the earthquakes, better optimize the behavior so that we can save money in design.
Basically, we're doing model tests. So we build a scaled down structure. We'll build a small scale building, maybe 1/20th scale or 1/50th scale. And that wouldn't, if you tested it at 1G, it wouldn't behave anything like the real structure, because the material properties are all different. But by putting it in the centrifuge, we increase the stresses and make it behave a lot more realistically.
Every model is designed for a specific G level. Not every model spins at 80 Gs. Some of our models may spin at 15 Gs, some may spin at 30 Gs, 60 Gs, 80 Gs. It's all in what they're designing and what they're trying to reach out of that model.
For every G force we add to it, it's like going down another meter in the soil. So instead of placing sensors in areas that are prone to earthquakes and waiting for an earthquake to happen, we can go ahead and simulate an earthquake in a G-force and get that data. How would this building react if an earthquake hit?
So this machine, by spinning around, it enables us to simulate the stresses properly. So we can get a much more accurate simulation by doing a model test on the centrifuge. I think we've made a lot of progress in that.
Oregon State holds the NEES Tsunami Wave Basin, the largest facility of its kind in the world for studying the effects of waves.
My name is Dan Cox, and I'm here in the College of Engineering here at Oregon State University with about 100 undergraduate students here to bring you the next generation shared use facility for tsunami research. As part of this project, we've tripled the size of the basin. It's now 160 feet long by 87 feet wide and 7 feet deep. And we have a large wave maker at the far end of the tank. And taken together This makes this the largest facility of its kind in the world for tsunami research. What I'm standing on here is a scaled model of an actual harbor in Puget Sound based on marine surveys. This is packed sand with a concrete cap on top, and it was actually built by our students here this summer as part of an undergraduate research program. One of the important things about doing this laboratory work is that we have very careful control of the wave conditions, and we can accurately measure the incident wave as it comes in from the sea. Behind me we have one of these wave gauges that's sticking into the water, and that'll measure the height of the tsunami as it passes. For a typical experiment, we would deploy about 15 to 20 of these sensors to give us a realistic boundary condition, and then also figure out how the wave moves as it goes over these underwater contours. What you heard behind me now was the tsunami coming into the coast. You can see it breaking on the shore, into the harbor, and then impacting the city. You can see all the debris has moved inland, and now you can see the water receding through the channel. And one of the important parts here is that sometimes the biggest forces are created by this receding water. For example, you could have a lot of scour that would cause bridges to collapse and that type of thing. What we'd like to show you right now is the versatility of this system. And you can see in the back here we're making directional waves that you would see, for example, out on the coast in the summertime. This motion is possible because the wave maker is segmented into 29 separate paddles, each one with an independent control system, and is capable of producing all kinds of waves. We can make storm waves, boat wakes, summertime swell, just about any condition you can imagine out on the coast. Here at Oregon State, we are truly excited about being part of the NEES program, and for the next 10 years being the nation's premier facility for tsunami research.
One of NEES's 7 large-scale testing facilities is at the University of Colorado at Boulder. This lab specializes in fast hybrid testing, a testing model that combines real-time physical experiments with computer-based simulation for evaluating the earthquake performance of structural components and systems.
Our facility is a fast hybrid testing facility. We couple physical testing with numerical simulation. We pursue that in an effort at consistent time scaling, which means that we're able to operate a testing structure where the physical test occurs in the same time frame as all the computational models are occurring.
We break a structure into 2 substructures, a physical one and a numerical one. So the physical one is the one which is least understood, and it is the one that we would like to test in the lab.
So we facilitate a researcher's ideas of how they'd like to see certain elements of a building structure tested by using real waveform data from previous earthquakes and included in the numerical component of a model.
Well, the issues that we're working on here are mainly concerned with correctly modeling materials in the building. So things like concrete and steel, sometimes it's not always easy to exactly model the way they would work in the real world. There's sometimes things like steel actually bending and then staying in that position are sometimes harder to analyze.
The way it simulates the real world is that we're using this physical structure that's embedded in this numerical model that simulates the real world circumstances of a building. And the physical specimen itself is exclusively a real specimen that would be used in a building, in typical building construction. So that's sort of a real world situation, as best as you can make a real world circumstance in a laboratory. So that's the advantage, in a sense, to being able to do this type of work. We don't have to build this huge building. We only have to test the one element that we know the least about.
The common thread among the facilities is the NEES Cyber Infrastructure Center, a service-focused partnership that operates and supports the extensive IT infrastructure used by the NEES program.
It's always been envisioned that these laboratories would be connected through a grid or a cyber infrastructure that would enable them to share data and to use supercomputers and start to make use of other technologies that weren't available to them at the time. And also because in earthquake engineering, they're starting to move to projects that are really distributed. So, you get researchers in Virginia who are working with researchers in California who are working with, even globally, and they need some kind of infrastructure in place to help them collaborate and do the research, that they never could do before in one location. So they're broadening the scope of their research, and in order to do that, we need to provide tools that enable them to communicate and collaborate together.
Our main focus here is to try and listen to the researchers and determine what tools we need to build to enable them to do their research. So a lot of it is understanding how they're using current tools and where we need to take those tools next.
We have cameras all over our lab that people from the world can actually be able to see what's going on in the lab and the testing.
So a person could be in the next room or could be 1,000 miles away or 2,000 miles away and still being able to receive data that's going on in the experiment.
You can have your experiment being seen by high school children and motivate them to become engineers. This is an opportunity that you wouldn't have before.
So it's really giving, it's I think changing the culture of how research is done, because now it's done more on a community basis and community sharing through community resources.
They have the IT capabilities to work on common problems at distance and in the analysis of the data. An important element of the collaboration is that the data and the information that's gathered is compiled and put into a permanent data repository we call the NEES data archives.
And at some point, other sites can go out there and grab that data again to reproduce experiments.
We're only in the beginning of the NEES 10-year Collaboratory, so we're still really in the gathering data stages. The cyber infrastructure is going to have a tremendous impact in the next few years when people actually start accessing the data.
The conventional way of writing your paper and publishing in a scientific journal and somebody reading it a year or two later is gone. It's going to be days, not years, before people will say, gee, that data shows we need to rewrite the book.
As long as we seek ways in which to create a safer future, the field of earthquake engineering continues to be an exciting, growing career.
Well, we do it because we're all curious.
Here, it's never a dull moment.
We do different things all the time. It's very challenging. It's a very challenging field.
Engineering is real-life applied math. We're not looking to solve some strange theoretical issues. We're looking to solve real-world problems.
We do both mathematical modeling and experimental modeling. Hope we can get the two of them to agree. And the net result is that building a safer bridge, saving a life down the road somewhere. So it can be a very fulfilling career.
I chose engineering because I think it's an exciting field. There's opportunities if you love math, you love science, you love technology. It's an opportunity to combine all that and think about how you can do things that either are for the public good or innovate, help to improve our economy and our competitiveness. But engineering offers you all those opportunities.
I think a good earthquake engineer is a person who wants to make a difference. They need to be a person that wants to do research for the purpose of change, wants to help people. We've seen that earthquakes can be incredibly damaging. And if somebody wants to be an earthquake engineer, it's a person that wants to make a difference in people's lives.
Earthquake engineers solve problems that save lives. And they do this on a daily basis. They use some pretty exciting equipment. They use really big machines. They simulate really large forces, and they use some of the most advanced information technology on the planet, and they push the envelope. It's exciting stuff to be involved in.
As long as we seek ways in which to create a safer future for our society, the field of earthquake engineering will continue to provide exciting and rewarding career opportunities. Although we will never be able to prevent earthquakes, NEES is increasing human safety and the resilience of society through its research efforts. By using advanced facilities, collaborating through cyber infrastructure, and building a repository of research data, we are able to design and build structures that will better protect society and reduce damage due to future earthquake activity.
For more information about the Network for Earthquake Engineering Simulation, visit us at www.nees.org.